Hi, my name is Martin Now. I work in the kernel team at Facebook. Today I want to share with you some of the Linux kernel issue in V6 that we have been seeing when we run V6 in production. I hope the solution we have will be useful to you too if you have to run V6 in your production environment. This one? Oh, okay. So when I just joined the Facebook kernel team, I was told that V6 has a scalability issue in the kernel. Being naive, my first reaction was, is it for real? I mean, who else is talking to us in V6 other than Facebook internal traffic itself? So I took a look at the V6 statistic we got to try to get a sense of how many end user is talking to us in V6. So the data I'm going to show you is the data I captured in 2015 when I started looking at that problem. So when I look at the problem, we had about 10% of end user talking to us in V6. If we only look at 4G, we had about 30%. Of course, for internal traffic, we are about 100% V6 only. So that was awesome. We have a lot of traffic talking to us in V6, except that we do run into a lot of kernel issue in the IPv6 stack. The first one I want to talk about is the one that I found the most interesting. It's about the IPv6 routing tree. So in the kernel, our V6 routing tree somehow is really big. It's huge because we have a lot of end users talking to us in IPv6. It was so big that it fell apart in production. A lot of bad things happened. The first one I want to show you is about a very simple command. Just print out the routing tree. The command is very simple. So here's the screen capture that I took when I run this command. It was captured from a machine that has a lot of end user traffic talking to us in V6. It's very simple, like IP-6 route. So just print out the route entries we have in the routing tree. It print 61 entries. But it took 11 seconds to just print out 61 entries. Can any one of you guess why it took so long to just print out 61 entries?
Really slow implementation of WC.
Good try. So the answer is in the next slide. The next slide is running a similar command in the same machine. The only difference is it append a table cache in that IP-6 command. What it really does is ask the kernel, hey, show me everything. The last command I showed you in the last slide, the kernel will filter out all the cache route, or what I call Kong route. But this command I showed you in this slide here is ask the kernel, hey, show me all the Kong route, or show me all the cache route. It turns out that the tree is really huge. Instead of 61 entries I just showed you in the last slide, the tree actually has 61,000 Kongs route in the tree. So that's why it takes a lot of time to just get all this data out from the kernel and then print it out to the terminal to you. So in this presentation, I'm going to use Kong route or cache route back and front, but actually I mean the same thing and they are the same thing. But I found the Kong route is a better word to use because it tells where it comes from. I'm going to tell you why it is in the later slide of this talk. After I learned the fact that printing out the tree could be pretty expensive in a production machine, just after a few days of learning this, my coworker asked me to investigate CPU issue in a production machine. And the report comes with a CPU graph looking something like this one. You can see the orange line is plotting the CPU usage of a script that we run in production. You can see the script has some CPU spike from time to time. The blue line is plotting the CPU idle percentage of that machine. You can see whenever the script runs, the CPU idle percentage of that machine goes down to the drain. So when we investigate the script further, it turns out that the script is running the same command that I just showed you in the last slide to print out the tree. I don't know why it is doing it, but it is legitimate to do, right? Who could think that when a command to print the tree, which only has 60 entries to it, will take so long and cost so much CPU to run? The only difference is this machine happens to have 500,000 cones in the tree. So it is really queuing the machine whenever the script runs in the machine. So after this incident happened, we declared that no script is allowed to print the tree. And I thought that's the end of the story. But you guess what? Sometimes we just cannot help it. Here's a screen capture that here's the source code capture I took from the Java openjdk. So what it does is it opens a file called IPv6_route. What this file essentially has is the whole routing tree in it. All 61,000 cone entry is in this file. The openjdk open this file, iterate through it. It burned the CPU and the end user suffer from it. Now, what I've told you is about the problem we hit when we try to print out or dump out the whole big, gigantic routing tree. The next problem I'm going to show you is even worse than this one. Here's a graph plotting the number of entries of the routing tree we have in one of the production machines. Essentially, it's plotting the tree size of the production machine. You can see from time to time, the tree size drop from a few 100K every time. So what happened is in the kernel, there's a garbage collector to clean up the tree from time to time. So whenever you run, the size of the tree becomes smaller. It sounds like a good thing, right? Because I just told you we have a tree size problem. The tree was so big, it took so many time to print it out. So the GC sounds to be a really good idea. It keeps the tree size under control. Except that whenever the GC runs, it took an exclusive log to the tree. What does it mean is when the GC runs, it took an exclusive log. No one can look at the tree. One of the side effects is it brought all the TCP three-way handshake from happening. And it took a long time for the end user to finish the TCP connection. It may eventually time out. And a lot of unhappy faces in your cell phone when you try to read the story from Facebook. So we used to have a few workarounds put in place to try to work around the issue. The first one we got is to fix the openjdk problem I just told you in the earlier slide. We call that in Java openjdk, you try to open a IPv6 route file which has the whole routing tree in it. So what we did is a very small C program here, which implement the fopen function call. And in this our own fopen implementation, we intercept whenever the Java openjdk is trying to open an IPv6 route file, and just return error to the Java openjdk. It was fun to us because in our production use case, it turns out that the Java openjdk doesn't learn anything useful by reading this file. So it's fun to us that we just return error, and it's fun. And we compile this little C program into a .so, and then use the usual LD payload trick to intercept the fopen system call, and it saved the day. And the second workaround we put in is we'll put in some hack in the kernel for not showing the cone route in the IPv6 route file, and also we try to limit the time it spent in one of the sprint log when the user application is trying to read the v6 row file. So the third one we have is about a sysctl. So our tree, we have more and more users talking to us in v6. So we need to set the max size of the tree to be bigger and bigger. I recall we set to a few hundred K, a million. Now we are at 8 million. And to be honest, I don't even know why we have 8 million, but it doesn't matter. Because by seeing this all right around I showed you, it's very obvious that we need to find a proper fix for it. So I was very excited. I was ready to optimize the garbage collection, how to minimize the tree size by compressing the tree, or optimize the logging mechanism in the tree. But before that, I still had a few questions in my mind that I don't understand. So the problem is, the question I have is why what's a cone? I mean, why there are so many cones in our production, and who created it, and when it is created, and why a cone is needed. So to understand what's a cone or when it is created, I ran a few of this command, IPv6 row command in my dev machines. The first one is IPv6 row show table cache. It's the same command that I used in the earlier slide to ask the kernel to tell me, okay, tell me all the cone row you got in the routing tree. When my dev machine just boot up, and before it start talking to anybody else, it should have zero cone entry in it. And then I run another row show command to tell what's the default gateway row of my dev machine. So it's a pretty standard default gateway. It's a default weird FEX0 link local address. Full depth if0. It learned from the RA router advertisement. It has a 64 hop limit in it. It's pretty standard. And then the third command I try to run is NC. I just randomly pick a 241 address and connect to it. And to the matter of fact, it even failed to connect because of the access rate issue. But it doesn't matter. I run the show table cache command again, and suddenly a cone row appear in the tree. The cone row is the same destination that I just connected to by using the NC command. Now the picture becomes clear. The kernel help us to create a cone entry for every destination address that a machine try to talk to. For example, if our web server talk to 1 million cell phone in v6, it will have 1 million entries. It will have 1 million cone entries in the routing tree. Now, if you compare the cone row and the default gateway row, you will find that they are pretty much the same. For the routing purpose, using the cone row or using the default gateway row, it essentially end up to the same location, right? It essentially end up to the default gateway router that packet should go to. So there's really no difference in using the default gateway row or using the cone row to route a packet. But then the next question is why a cone row is created in the first place if the cone row is essentially the same as the default gateway row. Sorry. And the answer is in this slide. So I capture some of the cone row in the production machine. It turns out that some of the cone row do have some difference when compared with the default gateway. The only difference is it has a small MTU here. I have highlighted here with the blue color. For this particular cone row, it has a smaller MTU, which is 1406 when compared with the default gateway. Now I think the whole picture is clear. We only need the cone row if if that particular destination have a small MTU. I believe most of you know in V6 how do we learn a small MTU for a particular destination. It's pretty much a router get a packet, and then somehow we cannot handle it because it's too big. Then you will send back a ICMP-v6 too big message with a small MTU in it, and the sender will learn the small MTU from the too big packet. So it is exactly what is happening. The kernel got a ICMP-v6 too big packet, learn the small MTU from it, and then update the MTU value to that Kong route. It can only update the MTU value of the Kong route because it cannot update the default gateway route because the default gateway is shared by everybody. Okay, so we learned that. We learned two things. One is most of the time the Kong route is as good as the default gateway route. We can just use the default gateway, but the Kong could be useful if that destination indeed has a small MTU. Now the next big question is how many Kongs of it has a small MTU? What do you guys guess? What's the percentage of it? You're right. Actually, when I look at the production machine, I was pretty surprised. I mean, for the end user traffic machines, we have less than 1% of them has a small MTU. And for the machine that only talk internally, I mean by internally I mean a Facebook machine only talk to another Facebook machine, it does not have Kong at all. So we created a lot of time, memory to create a Kong for nothing. So I also talked to one of the Linux contributor, the kernel contributor, who worked for a Linux distro. He also has a customer which run a DNS server at a V6 machine, and that customer is seeing a similar problem that we're seeing, and they're using a similar hack that we're doing. By learning all this fact, it totally changed the strategy on a fixed way. The origin thought was optimize the GC, minimize the locking mechanism, minimize the tree size, things like that. So now we took a totally different approach to the fix. So here's my first attempt. The solution is pretty obvious. We don't always Kong. Instead, we only Kong when we receive a ICMP-v6 message. Just by doing this, 1 million Kongs in our production can be removed, and we can keep using the default gateway route. So it's awesome. 1 million Kong become one default gateway. It's a lot of saving. The first one of functional tests were fun. I was very excited, and I was about to post it to the upstream. But the happiness only come until the happiness end when I got a benchmark result that showed more than 50% regression when it tests under 40 threads test. I got this result at the weekend, and I was so disappointed. I told you it's attempt number 1 here, but actually it's version 10 in my local Git repo already. So I closed the laptop. I forgot about it. On next Monday, I pull myself together and I look at the performance test result more closely. Now, one interesting fact I noticed is I run the one thread test many times, and it does not show any performance regression. So it got me thinking, and I started to suspect there must be some contention somewhere in my approach. So after looking at it further, the contention comes in when the contention is at the reference count. So each default gateway route has a reference count in it. So if all the CPU share the same reference count, it will cause a lot of CPU bouncing between different CPU, and that is where the performance loss. Sharing usually comes with a cost, right? So there's no free lunch. That's the same case here. And in production, we do have a lot of CPU. that's why we saw the regression is pretty bad in the first attempt. So by learning this fact, I make some changes to my first attempt. So here's my second attempt. So instead of all the CPUs share the same default gateway role, we make a copy of the default gateway role for each CPU. If we have 40 CPU, we will have 40 copies of the default gateway role, so that each one use their own reference card, and the reference card pretty much stay local to that particular CPU. So we remove a lot of CPU cache bouncing by just doing this. So after this, the performance on the 45 test come back. So I was so excited to run it in the production, and that's the result before and after the fix. Here's the same graph plotting the tree size of our production machines. So before it's pretty much the same. The tree string from time to time, and after the fix, the line is the tree is so small that it's really difficult to see somehow. But there's a good problem to have, and there's an easy fix. I put the same graph in not scale. Now it's much more clear. Before, every time the GC run, the tree string from 400,000 to 200,000. So every time the GC has to clean up 2,000 entry from the tree. After the fix, whenever the GC run, the GC only have to clean up 400 entry. So the tree string from 1,000 entry to 600 entry. So every time you only have to clean up 400 entries. It's a multiple magnitude improvement after the fix. So all of this I've taught you about, it has already been upstream. Is in the 4.2 kernel, if I remember correctly. So I was pretty happy. So now the fix that I just told you is some pretty fundamental IPv6 fixes. It touches many systems, so it is unavoidable that it breaks someone else's use case. But we have been working with the upstream very closely to understand what cases they break, and we provide fixes for them. So here's a sample of fixes, a sample of follow-up fixes that we provide to the upstream. So now I want to switch the topic a little bit. I want to talk about what other IPv6 feature or fixes that we contributed to the upstream. Now, the first one I found is very interesting is called Identifier Locator Addressing, ILA. It was proposed by my coworker Tom Herbert. So it has an innovative use of the whole 128-bit IPv6 address space. So instead of giving a fake address or private address, IPv4 address to every VM you may run in your host, why don't we give a true IPv6 routable address to your VM? So we smartly split the address into a locator and identifier. And Tom has written a very nice ITF document. You can go to take a look on how he is proposing to use IOA to solve the virtual addressing issue without encapsulation. The next improvement we did is also about a routing tree. We remove a router log we remove a writer log from one of the fast path. So it improved the benchmark test by 70%. The benchmark is testing how many lookup you can do on the routing tree. Now this one I also find very interesting is in the V6 routing tree. Some of the route can suddenly disappear. So it was reported by Ying from Huawei in the mailing list. So we took a look at it. We understand the problem. So what happened is he has a manually configured V6 route in the routing tree, and after the kernel received a ICMP V6 2-bit message, the same route suddenly has an expire value in it, and then the route got disappeared after the value expired. So what happened is the expire should only mean she expired the MTU instead of expiring the route, but the kernel mistakenly expired the whole route itself. So we produce it and we reproduce it and we fix it, and we also contribute back to the upstream. Now the next problem we hit is about V6 GRE. So we have a V6 GRE use case to do load balancing. In our scale, it's very easy for us to hit the race condition in the GRE tunnel in V6. It turns out that this bug was there at the beginning, at the day one, when IPv6 in the kernel. So here's the list of fixes we provided upstream to fix the issue. The next one, the last one is about turning something on by default for IPv6 in the kernel. I found those are small changes, but very meaningful change. It sends a signal to the community that, hey, IPv6 is mainstream. Please test IPv6 if you're making TCP change, or if you're committing new driver to the kernel, please test IPv6 because it's important. And it's so important that we even turn it on to make it compile by default. Now going forward, we're still observing TCP accept is 10% slower in V6 when compared with V4. We want to adjust that. Another thing we want to adjust is in the V6 forwarding tree. Right now it's using a read-write lock. We want to replace it with a much faster RCU locking mechanism. The last slide, I want to spend some time to talk about other Linux kernel projects we have been working on. All this project has been upstreamed or has been discussed with upstream. We have a upstream first approach. Whatever we do in the kernel, we will push it to upstream first before it really hit our production in scale. The first one is KCM, Kernel Connection Multiplexer, which is proposed by Tom also. So if you know TCP socket is a byte stream API. So KCM socket is a message-based API. So it will give you, instead of giving you byte by byte, it will pass the message and then give the application the whole message in one shot. Another one we are working on is putting TLS in the kernel. The third one is about express data path and BPF, which is proposed by Alexei. Oh, by the way, TLS in the kernel has been working on by Dave. Okay, so go back to the XDP and BPF. It's proposed by Tom and Alexei. So what it's trying to do is some of the use case in the kernel is like dropping a packet, forwarding a packet from ETH0 to ETH1, or forwarding a packet from your host machine to your VM machine. It turns out that the current kernel is not fast enough because it has to initialize many things and assume that packet will be processed by the host application itself. But for the case that I just told you, simple forwarding is not the case. So we are trying to create an express data path and using BPF to realize most of the functionality. The last one I want to talk about is about TCP. We are trying to make a few TCP changes to make HTTP2 response time measurement easier. All of them has been pushed to upstream, and most of them has LWN coverage. You can search it, and they have a lot of good articles talking about them. All right, I think that's it. Do you guys have questions?
Hi. So regarding the flow labels, you said you're going to turn them on. We turned them on in all of Apple products years ago. We didn't see any problem with it. But I'm not sure if it's actually helping routers, or if it's actually helping the other vendors to routing all of our IPv6 packets, because I have no feedback from that. Do you have any feedback? Is that the reason why you think turning them the flow label on is going to help, or do you have other reasons too?
I think our main use case for having flow label on is doing the ECMP thing. But we have been trying to roll out in the for the internal traffic. I don't have a lot of experience in the end user traffic yet.
Hello. Great presentation, thank you. My question for you is this a potential DDoS vector? Even though you've added your fix, could somebody forge the packet too big messages and just fill up your route cache again, unbeknownst to you?
What do you mean? Can you...
Oh, sorry. So my understanding is part of your fix is to only insert a cache entry if you get a packet too big ICMP error back, and it's lower than the MTU.
Okay,
right?
I got what you mean. So, I think there are two ways to answer this question, right? I mean, the first one is for TCP. For TCP, for example, we only accept a too-big message if the sequence number is within the window, right? So that mechanism already protects to a great deal. And the second way to answer the question is if we don't do that, we're DDoSing ourselves. I mean, we create so many for whoever we talk to. So that is the fix to stop DDoSing ourselves. But how to defend ICMP too big is a different problem.
Cool. Great. Thanks.
Thank you very much for sharing this. A lot of great information. Any experiences with using IPv6 NELP filter and connection tracking in the kernel as well?
We don't use connection tracking. Yeah.
A quick question. Earlier, I asked why Facebook run the BGP session between servers, like from server to network gears. And I was told because for the traffic engineering, so controlled by the server, not by the network gears. But now you are saying majority routes are actually default gateway. So then the question again, so why bother to run the BGP to the server level?
That's only to solve the problem. I simplify the problem a lot. But definitely we have more route than default gateway.
Maybe you can elaborate on the very last slide you put up of some other fixes you put in for H2 and TCP measurement. I'd be interested in.
Oh, the TCP and HTTP2 measurement.
Yeah.
So what we're interested in is so when a web server sends an HTTP response, we want to know from the first byte. We want to know when we want to know the true response time per se. So we want to measure the time when we write the first byte of the response to the socket to the end of the response, right? But how do you define the end of the response? I mean, for now you can only define it by I finished writing the last byte to the socket. But that's not the real response time, because the real response time is you have to measure till the TCP ACK come back to your last byte. So we make changes to TCP to measure this TCP ACK to the HTTP2 response last byte. So that's the time span we are measuring. Yeah.
Hi. So you talked briefly about ILA. Are you deploying? Where are you? What are your kind of findings? The identifier locator addressing?
Wait.
Tom's draft.
Tom, yeah. What's the question?
Are you deploying? Are you testing? Where are you? What's going on with it?
I think we're testing it. Yeah.
Any feedback?
We're in testing right now. I don't think we have much feedback on it right now. It's still pretty much in early developments, but it's our hope that this will eventually replace all host-host communication, and part of the reason why we need a /64 per host.
ILNP is dead, sir.
I'm not a kernel expert, so this question about it will make sense. But I was wondering about the scalability of the solution you mentioned before, the per CPU reference count. So can you please comment on the scalability with regard to two aspects? First, what is the maximum number of reference counters that you can keep per CPU? So if there is a limit, maybe you cannot store as many, route caches per CPU. And second, whether there is an extra cost if you need to go and update all of those routes in all of the CPUs. Thanks.
Can you repeat the first question?
The first question is, per CPU. Yeah, you are using a per CPU reference count. If there is a limit, or if there is a byte limit of per CPU counters or per CPU data that you can store, that would essentially limit the number of entries, route entries you can track per CPU.
We haven't hit that limit yet in our scale, so I hope we won't hit that forever. For the second question, what was the second question? Sorry.
If there is an extra cost when you need to
okay. Yeah, right. So it will take more time to update for sure, but we don't update the route very often, right? So, but the update is not as expensive as you think of. It's like you have, for example, default gateway route. We have one default gateway route, and then we will make 40 copy of this gateway route, and we don't make it every time we change. We only make it if there's a lead for that particular CPU. Okay.
Martin, I think he's wondering, all the cloned routes are not per CPU.
All the what?
You said that the default gateway is per CPU, but the cloned routes are still shared across all CPUs.
Yes, the clone route is still shared across the CPU.
So we don't have 40 copies of the clones.
Yeah.
It's just the default.
Because the clone route has much less contention, right? It won't be. It won't be common that all the CPU want to talk to the same destination per se. Yeah.
All right, thanks, Martin.